Good morning. I'm very conscious I'm standing between you and lunch, so I'll try and move along as quickly as possible. By way of introduction, my name is Andrew, and I'm a recovering type theorist. What we're going to try and do in this talk is explain to you how inheritance works as an aid to program understanding. And let me be quite clear up front, I'm not going to talk about the formal properties of inheritance, and neither am I going to talk about types. In the introduction to the paper, we're quite clear that our emphasis is on the value of inheritance as an aid to human understanding and not on its formal properties. This is quite deliberate and we believe long overdue. We've known since 1989, Cook and Paulsberg showed that formally inheritance is equivalent to parameterization. That's not in dispute. But I think that has led language designers, particularly designers of functional languages, to regard inheritance as unimportant, unnecessary, or even undesirable. They argue, quite correctly, you can simulate inheritance using higher order parameterization. But that's not the point. Two formally equivalent mechanisms may be quite different with respect to the way humans understand them. Yes, Phil? Yes. Well, I think that was exactly what Will Cook did in his thesis. And that was where this paper came from. And it's been in the literature for more than 25 years. But I'm not going to talk about types.
There's your first mistake.
So in trying to establish the value of inheritance, I have to admit that the object-oriented gang doesn't always help either. In particular, this gang of four people who wrote a very well known book say right at the beginning in the introduction, here on page 20, favor object composition over class inheritance. You shouldn't have to create new components to achieve reuse. You should just be able to assemble existing components through object composition. And I have been challenged, even your own team are saying you don't use inheritance. And that's perfectly true, they are. Of course, if you look and read through to the next sentence, reuse by inheritance makes it easier to make new components that we compose with old ones. Composition doesn't actually work in practice because the things you're composing don't quite have the right functionality you want. And inheritance lets you modify that. So it says objects, inheritance and object composition work together, and that's exactly the way they're mostly used. So the problem I'm going to address today, as I've said, is explaining the value of inheritance, especially to functional programmers. I'm going on the assumption that I'm greatly outnumbered in this room by functional programmers, particularly higher order functional programmers who have been brought up with their mother's milk to believe that abstraction is good. And conversely, concrete things, well, not exactly bad. After all, we all do need to eat, but not as good. And there's a tendency when explaining new ideas to say, here's this beautiful abstract thing. Admire it. And that's it. Until someone in the front row says, but wait, can you give me an example? Has that happened here? Examples are actually what we use to understand. Examples are really important. Once you've understood a few examples, then you can form the abstraction. And once you understood the abstraction, you tend to forget about the examples. But it's not the way you grasp abstractions at the beginning. So rather than going from the abstract to the concrete, what I'm suggesting is much more effective to start with a concrete thing, often two or three concrete things, and then move from there to the abstract. And this is what I do when I'm teaching. I suspect you do it as well. So the story of this paper started, as with many stories, with this paper of Phil's, The Essence of Functional Programming, from Popple 1992, which, of course, as you all know, says that values and computations are different. You can represent computations with monads. Computations produce values, but they're not the same thing. This paper itself mirrors an earlier paper of Reynolds on the essence of algol, which says that in algol you have expressions and you have, I forget what terms he uses, but again, two different kinds of things, and algol 60 is not orthogonal. The things you can store and the things you can compute are different. So, and in the beginning of this paper, Phil asks this important question, shall I be pure or impure? Similarly, I'm going to start with a question, shall I be abstract or concrete? And abstract programs are more general, have more potential for reuse. But concrete programs are simpler, easier to understand because they solve the problem at hand more directly. So you have to make this rather difficult choice, in the same way that you have to make the choice between pure and impure in choosing your programming language before monads. Yes, I'm going to do exactly that. In fact, this talk is nothing more than an example. Okay. So inheritance, let's just avoid this unsatisfying choice. But I'm doing a little bit of a preamble first because I want to start in the right place. Inheritance also is not subtyping. So I have to say this because some of the reviewers of this paper said, oh, you should be clear that what kind of inheritance you're talking about. It's like, what do I mean, what kind of inheritance I'm talking about? Oh, they thought I meant subtyping when I said inheritance. Well, no, when I say inheritance, I mean inheritance. And when I say subtyping, I mean subtyping. And they're different. And we've known they're different for 26 years. So, as I said, I'm finished. I'm not talking about types anymore. But to help me make this distinction, I'm going to use a language called Grace, which some of you know that Kim and James and I have been working on for the last 5 years or so. Grace makes a very clear distinction between inheritance and subtyping. And it's also gradually typed, so I can write my examples without many types, but I can put in types if I think they help. Okay, so one last preamble mention. Inheritance is not about accidental reuse. Now, a lot of stuff has been said about this, written about this probably. I think it's highly unlikely that an object that is not designed to be reused can be reused. Inheritance doesn't make this possible, nor does any other mechanism. What you can do is you can take that thing that wasn't designed for reuse, refactor it, change the code, edit it to facilitate reuse, turn it into something else. And often your first sketches of things will not by themselves be reusable. You have to refine them. That's okay. But there's no magic here. And I'm not claiming that there is. Okay, finally, some examples. So there's actually 3 examples I'm going to work with. In the paper, there are 2 examples. One is evaluating expressions with and without various monads. And these are exactly, well, they're not exactly the same examples as in Phil's paper. They're the examples that came out of one of Phil's talks based on that paper sometime later because it improved the notation. And as we've established, it's always good to improve the notation. And the second example is the Erlang OTP platform, which is in fact the example that I was working on with Phil in this building 5 years ago when I was here on sabbatical. That is the genesis of this talk. I'll talk a little bit more about that. But the place I'm going to start in this talk is with mutable queues, because John Hughes gave a wonderful introduction to mutable queues on Monday, so I can assume you all know the basics of queues. This is a difficult concept, I understand, because they change. But it's a simple enough example that I can show you what I'm talking about without getting lost in the details. And these 2 you can read in the paper. Okay, so what is a mutable queue? So you create one in Grace something like this: var number q. Number q is a variable. We know it's a variable because we say var. And then on the right-hand side, we take some q module and we make the empty request on it. And what that gives us back is a new empty q. Now, I've been warned that this may be confusing to people who are used to immutable objects, because it doesn't stay empty once you put stuff in it. Right? But it starts off as empty, and that's why it's called q.empty. Okay? And that makes us an object. And this box here is an object. I was talking to David Turner at the break, and he said he never really understood objects. So tutorial on objects, this is an object. It's a line. It makes a distinction, if you're familiar with Spencer Brown's laws of form. The inside versus the outside. Stuff that's in the object goes inside and you can't get to it from the outside except through a well-defined interface. That's really all you need to know about objects. Okay, so inside this object, we have some allocated memory. It's an array. It's indexed from 0. And the idea of this queue is that we put stuff in it. We put stuff in from the right, and we take stuff. There's another one. It's not a very interesting queue. I'm only going to put numbers in, but it's an example. And then we take stuff out from the left. That's all we can do with this queue. I think we can ask how many elements are in there. Here's another one. So that's our queue data structure. And of course, at this point, the queue is full and we have to do something. And the refinements I'm going to make on this queue have to do with what happens when it's full. Okay, so here's the first version. And this is your first exposure to some Grace code. So if I can point things out, this box is a file. Represents a module, and it's also an object, because it's a file before you compile it. After you've run it, you get an object. Inside that object, we have a class. This class is called empty. As I said, it's called empty because when you invoke it, you make a new empty queue. And maybe in Java, you would say, I don't know what you'll say in Java. I'll go there. Inside this queue, what do we have? Well, we have an initial size, which is 4, so it fits on the slide. We have some elements of that initial size. That's just an array, primitive memory, if you like. And we have 2 indices. The first one points to the first element of the queue, and end index points to the element of the array after the last element. Right? So the difference between them is the size, and initially the size is 0, and they're both pointers are at 0 because the queue is empty. Right? We can tell it's empty because first index is last index. It also has a method capacity, which is different from size. That's the amount of space. It's good to keep track of these 2 things in the array. And we have 2 methods, add and remove. We can add an element. Well, assuming if it's full, we better do something to make more room. Otherwise, what do? Well, we insert this element at end index, which was the element past the space, put the element there. This is an array update. Arrays are objects, so we put E at that index, and then we increment the index. And to remove it, well, we better check that it's not empty. Otherwise, we extract something at first index and then increment the index. Right? So really simple code. Remember, Grace is designed for teaching first-year computer science courses to people who've never done much programming before. So although this is completely trivial to you, it may not be trivial if you've never programmed before. Okay? And then scroll up a little bit. There's some as string methods and as debug string so we can print stuff out. And here's make more room. What does it do? Well, it makes a new array of twice the size, copies stuff across into the new array, and then assigns the new array to the instance variable that held the old one. Okay, and there's some helper methods to test whether it's full, to index, to increment, to iterate through the indices, and to do the increment. Confidential means it's not exposed to the outside world. Okay, so you don't have to, in fact, understand all of the details of this, but it's a pretty simple data structure. All right, so let's look at what happens to make room when it's full. Inside the object, we have this array. So what do? We get a new array, twice the size. For all of the used indices, which are just 0, 1, 2, and 3, we just do the right thing. We copy those numbers across. And then we do this assignment. Elements gets new elements, so we point it down to here. That means the old one gets garbage collected at some point in the future. And we're all set up now. We've got space. We can insert the new element. So everyone's happy. Of course, you're not happy, but first your students will be happy. Right? We can just keep on putting stuff in the queue. Used indices do. It iterates through the indices that are used. So it abstracts away from the first index plus 1, first index plus 2, am I less than index, end index stuff. Well, let's go back and look at the code. Use the indexes do. It starts at first index and you repeat size times, do whatever you're doing, and then increment. This is the definition of used indices do. Right. It's a helper method that takes away some of the details of keeping track of the stuff, because I use this in several different places. I don't want to repeat that index arithmetic. Okay. So now, of course, we have to watch the animation again. But it's a nice animation. So yeah, and then now we can go sort of off to the races, and we can insert more stuff in the queue, and so on. Okay. Now, of course, you're all saying, but this implementation wastes space at the start of this internal array. We can never recapture that space. It's a queue. You never put stuff back at the beginning. You only in-queue things at the end. So the obvious optimization is when we're doing this copying into the new array, we should slide the elements down to the left-hand end. So it looks like this. The better plan is we make our new array, double the size. We copy these down to the beginning. Like 4. And then we get rid of that one. And then we can fill up from here. Now we've got more space, so we'll actually do less allocations, and that's good. So here's the code that does that version. It's different, of course. It's different in that now we have a second index j, and inside used indices do, we start j at 0, we increment j. So we're always copying to 0, 1, 2, 3, rather than whatever the old indices were. We don't care what the old indices were when we're doing the copying. So this method's got a couple of lines longer, but we're recapturing that otherwise wasted space. So we like this improvement. Okay. Here's the place where inheritance comes to our aid. How do we install this better plan into the code we already had? Well, of course, you can do it with Emacs. Exactly. Emacs is the Turing tar pit of computing. Right? Everything is possible, nothing is easy. When you do it with Emacs, you of course lose the old version. The point here is we can keep both versions around. We take that code, we embed that inside a new class which inherits from the old one. So this looks very similar to what we had before. We import the old queue. Remember, each of these boxes is a file. So we can import that queue, we grabs the file, names the object it gives us original queue, and now we can have a new class, which also is called empty, but that's in a different module. Module is called queue plus slide. We inherit original queue.empty, and we override the method make more room. And that's all that goes in this module. We don't have to say nothing else changes. We don't have to repeat the code that's already there, which copying code is bad, remember? We just say, okay, we now have a better queue. It's queue plus slide because it does this sliding action. And that's all the code we need, right? Yes. What confidential means is people outside your organization can't get to it, but your classes that inherit from you are inside your organization. They can get to it. So explicitly, confidential things can be accessed by your inheritors. So you may not want to look. I may not want to let you look at my bank accounts, but my children can. Yes. That's right.
You do that.
That's right. That's right. Yes. Because the blind alleys were lessons on the way to where you're going. So you don't have to follow those blind alleys if they're not useful lessons. But if they're useful incremental steps in building up your understanding, then that is in fact an advantage. No, it is executed because the first version of the queue runs. It's not something that's abstract and not runnable. And I run it when I run my tests, and I can show it to my students. And yes, so we'll get back to this point again. Oh my goodness, I've really had 23 minutes. I didn't have, no. Okay, so said this is actually a module. What to notice here is inheritance combines new code with, if you like, the editing instructions that say where to put it. The part being replaced was not originally declared to be a parameter. We turned it into a parameter at the place we overrode it. So take that constant, that piece of code that was fixed, let's make it a parameter. So inheritance, we call in the paper ex post facto parameterization. About as much as my Latin lets me do. Inheritance lets us focus on the changes. Now contrast this with what Wadler does in the essence of functional programming. He says, introduces an improved monad that has more features, and then he says, to modify the interpreter, substitute monad E for monad M, replace each occurrence of unit E wrong by a suitable call to error E. He's giving us editing instructions because his language is not able to express the kind of incremental change that he's found useful in the paper for pedagogical reasons. Inheritance provides a packaging mechanism for deltas. Inheritance is code plus the editing instructions. And I'm going to argue that both the super and the subclass are units of understanding. They can both be understood by themselves. Right? The superclass actually runs, and the subclass is, this is the change we make to make this improvement. How do you explain a complex artifact, Simon? Break it into simpler subthings. And that's exactly what I thought you'd say. So you break it into simpler things, you explain the complexities in the simpler things one at a time, and then you compose them. And that's what I'm doing here. It's exactly what Phil does in the essence of functional programming. It's exactly what Armstrong does in programming Erlang. It's what I do when I teach a class. And I suspect it's what you do when you teach yours too. So the consequences of this, of course, are that you can't see the whole object in one place. This is true. Behavior of an object defined using inheritance is distributed throughout the inheritance hierarchy. This is a feature, not a problem. Meanwhile, somewhere in Britain, people are standing in a queue. So, how do we recycle space? Once we see the idea of sliding elements to the bottom, we should ask, why do we allocate a large array at all? We have space here. Why don't we use it? So our next refinement, of course, is say, oh, there's space. Let's just slide the elements down. And then we can, we don't have to allocate a larger array. We've made more room by doing that, and we can fill it up. Okay. Can we add this feature to the original queue using inheritance? Of course, the answer is yes. Otherwise, I wouldn't have asked the question. And here's the incremental change. This is a bit more difficult, more extensive at least. So here's our new make more room. It checks the threshold. If there's enough space already left, it slides in place. Otherwise, it enlarges. Slide in place just takes user indices, slide things down to the beginning. Essentially seen that. What does enlarge do? Well, enlarge is in fact exactly the old make more room. So we have this language feature called an alias. When we inherit it from original queue.empty, we alias make more room, we give it a new name, enlarge. We then override make more room So this is the old make more room, the inherited one, and we can call that here. Other languages have a feature that does very similar thing called super. Super is very complicated. Most programmers don't understand it. So we've taken it out and we've put in this simpler alias mechanism instead. Okay, but it lets you rewrite the new version in terms of the old version. So you knew what enlarge did. You know what make more room did. That's now enlarge. And this isn't a refinement of it. It's built on it. Of course, you have to understand this part in order to understand that part. Why the effort you spent in understanding it is not in fact wasted. The investment that's paying dividends. Well, of course, you're all smart people, and you've seen John Hughes's talk. Why are we doing this sliding at all? We don't have to do it. We can treat elements as a circular array. So here's the version that treats elements as a circular array. It's actually simpler than the changes are less than the others, but we have to override 3 methods. We're still overriding original Q. We inherit from it. We change size to be modulo capacity. We change increment to be modulo capacity. And we change is full to check if end index is first index minus 1. I'm using the trick that I learned in Computer Science 101, which is if you leave an empty, one space empty in your circular buffer, then you can tell the difference between full and empty queues. So I avoid John Hughes's bug. And percent actually does do modulus in Grace, so we get the right answer. So that's all happy. The method overrides, these 3 overrides implement the changes. And here's some tests. You see I actually import all 4 versions of these modules here. And for each one, I run these tests with a different value of the Q module. So this is Q origin, Q arrange, Q slide, Q recycle, Q wrap in sequence. I run all those tests, and there's more tests here. And I get some output. This is the first version. This is the second version. And these are the debugging prints. This tells you which elements are full. This tells you the actual allocated size. So in some of these cases, the size goes down as we make the improvements. No. Yes, I'm not pulling wool. No, I didn't. I'm not claiming that inheritance for accidental reuse. Usually, code must be refactored to provide the hooks for inheriting object override. I don't claim you have to be omniscient to use this mechanism, because I'm not, and I use it. So this is what happened. This is the version of the code I wrote first time around. I didn't have used elements do, and I didn't anticipate all these changes. So I don't know if I can see the color bars. I don't know if you can see them on the projector. But this is the version that you've just seen. This is what I started with. And the diffing shows you what I actually had to change. So yes, I made changes. I had to refactor the original code to provide the hooks that I overrode. But these hooks themselves are useful. It's much clearer to say if is full, then make more room, than if some mumble with index manipulations and elements of whatever. Right? This is an improved version. It's much better to say used indices do than actually have something here. First to this -1 reverse mumble, which turned out to be wrong, by the way, because I was printing out the queue backwards. It is more abstract. Right? We've abstracted over these things by providing what Kent Beck calls intention revealing names for pieces of code. Right? That makes it good. Right? It's not, it may seem more abstract, but in fact, these pieces are just defined a little bit further down. Right? They're concrete pieces of code that are there. They just have names that tell you what they're doing. Right? I think I don't have time to answer questions right now because I want to sort of get to the punchline. Right? They introduce intention revealing names. They improve communication as well as enabling inheritance. I'm not claiming that I'm omniscient. I'm not putting any wool over your eyes. Right? There is nothing up my sleeve. So I don't think I can talk about Armstrong's explanation of the Open Telecom platform because Connor is bigger than I am and has a deeper voice. But take a look in the book. What you'll find there is there's a bunch of stuff that has to do with the explicit state, which is why Phil and I got involved in this. But essentially, go through these. What's here is the basic server. Armstrong gives you a page of code describing the server. Then he adds transactions. He gives you a page and a half of code, rewriting everything you've already seen to add transactions. Then he gives you a server with hot code swapping. Rewrites everything from scratch, again, adding, now it's about a page and 3/4 of code with hot code swapping. Then he does a 4th version, which includes both of these 2 changes. And you, as the reader, have to sit there and do diff in your brain to figure out what he's done. So I couldn't understand this, and I went off and up to my office on the 4th floor, whatever, and I sat there with a Smalltalk implementation, and I coded this up in Smalltalk, and I thought, oh, I can get reuse here. I can use inheritance, and now I understood the changes he'd made each time around. Right? And it was this isn't complicated at all when you break it into small steps. So I think I better cursor back here. So summarize, our thesis is the essence of inheritance as it lets us go from the concrete to the abstract. It does this using ex post facto parameterization. Why essence? Essence is a property of a thing without which it could not be what it is. So I'm not claiming that this is the only way you use inheritance. But I am claiming that nothing else does this. The essence of inheritance is its ability to override something that's concrete, something you didn't initially declare to be a parameter. We certainly use inheritance as an abstraction mechanism. We write abstract classes and then we subclass them, knowing that that's what they're for. Right? There's even syntax in Java and in Grace to say this thing is a parameter. It's a required method. It's an abstract method. When you use inheritance like that, it's a parameterization mechanism and a fairly clumsy one. The real value of inheritance, I'm claiming here today, is you don't have to use it like that. You can actually use it to do this ex post facto parameterization, and that's where it's novel. And my conclusion, this is a wonderful quotation that I like. It's from an essay you should all read, Alyssa Baniasad and Clayton Myers, An Exploration of Programmers' Language. When we write a program, we're teaching a new language. Let's use all the pedagogical tools we have. Inheritance is one such, and if it's not in your toolbox, you should talk to your language designer. So thank you, Phil, for the inspiration that went behind this talk. Happy birthday. It's a pleasure. It's a pleasure to be here.